In this video, we're going to go ahead and talk about how to simplify radical expressions. Now, to be honest, this is best learned by working a lot of examples, so if the examples in this video aren't enough, be sure to try to work your own. So, let's go ahead and work an example. Let's simplify each of the following radical expressions. So, the cube root of 24, always we should try to actually take as much of the roots as possible. So the cube root of 24, the easiest way to do this is to figure out which factors can we actually take the cube root of. To do this, let's go ahead and use something called a factor tree. Now 24 is divisible by 2, so 2 is a factor, and once we take 24 divided by 2, we get 12. We can further divide 12 into 3 and 4, and then 4 is 2 times 2. So, what we have here is 24 is really the cube root of 3 2's and 1 3. Now, anytime we have 3, because it's a cube root, 3 of the same factor, those can actually come out to the front. Basically, we're taking the cube root of those, and we end up with 2. So we have 2 times the cube root of 3, and now we go ahead and we stop because we can't do any more. We can do the fourth root of 48 in a very similar way. 48 is the same thing as 2 times 24. So just a pro tip, when you're evaluating these, if it's an even number, it's always divisible by 2, so go ahead and divide it by 2, and then just work from there. 48 divided by 2 is 24. We already did the factor tree for 24, so what we notice here is that we have a 2 and a 2, so this is the fourth root of 2, and then 3 2's, and then a 3. Well, since this is a fourth root, we can pull 4 of those 2's out and to make 1 2 on the outside, and then we're still left with that 3. 75, a factor tree for it would be 75 is, it's 3 times 25, so 3 and 25. 25 is a perfect square, so it has 5 and 5. So what we actually have here is we have the square root of 3 times 5 times 5, and then we have 3 x's as well multiplied together. Now, this is a square root, so we need 2's. We need double factors. Those can come out. Now, an important thing here, when we pull the 5 out, since this is an even root, and we actually should have done this here, but we didn't because it's a positive number, but when we pull the 5 out, really we're putting an absolute value on it, but absolute value of 5 is 5. And because this is an even root though, we also have that the absolute value, when we pull the x out, we do need to put an absolute value on it because we don't know what it is, what value it is. It could be negative. But a 3 and an x are left under, and so that would be our answer. Moving along, 24, already did the factor tree for, isn't that handy? And we have 3 2's, so we have 2 times 2 times 2 times 3, and then 4 a's. 4a times a times a times a. And we're taking a cube root. So, when we do that, we end up with, we have 3 2's, we need 3, because that's our index. 3 2's, they'll come out, and then we have 3 a's, those will also come out, and I don't need to put an absolute value on them because this is an odd root, not an even root. And I'm left with a 3 and an a under the square root, the cube root. Finally, for this problem, 5x to the fourth is just 5x written out 4 times. If we regroup things, we end up with 5 times 5 times 5 times 5 times x times x times x times x, which is just a 5 comes out and an x comes out, and we have nothing left under the root. So because of that, we just we can drop the root. Really what we're doing is we're taking the fourth root of 1, but the fourth root of 1 is 1. Any root of 1 is 1. However, you'll notice here that this is actually a little bit easier. Actually, I made a mistake first. First to remark, this is actually absolute value of 5 and absolute value of x. And so, again, what we actually have here is what we could do is we could use our property that we used before. Namely, we could have just written this as absolute value of 5x. Absolute value breaks up across multiplication, as we saw long ways back. And absolute value of 5 is 5, so we have 5 times absolute value of x. So sometimes there's an easier way to do some of these problems using those radical properties we talked about in the last video. So now it's time for you to try an example. Go ahead and simplify each of the following radical expressions. Again, on the count of 3, I'll reveal the answer. 1, 2, 3. So now you can go through and check your answers. Just a couple of remarks. Here you'll notice I had the -3's written out. A helpful thing here is if you see a number with a 5 or a 0, you know immediately it's divisible by 5. And here we actually did pull out each of those absolute values, but as we saw before, when you do the absolute value squared, even if it was negative, it would have canceled, so it always would have been positive anyway, so we can drop the absolute values. For another example, let's go ahead and simplify each of these radical expressions. Now, if we break these up, 48 we can divide by 2. We did this already, but might as well do it again. 24 is 8 times 3, and 8 is a perfect cube, so 3, 3, and 3. Or no. 8 is a perfect cube, so 2, 2, and 2. 27 is a perfect cube, and it's 3, 3, and 3. So what we actually have here is we have that this is 2 times the square root of 2 times 2 times 2 times 2. Let's go ahead and section this off as a side work. 2, 2, 2, 2 times 3 minus 3 square root of 3 times 3 times 3. And again, we know that we can bring out pair since it's a square root. And so this is 2 times 2 times 2, square root of 3, minus 3 times 3, square root of 3. Simplifying, we have 8 square root of 3 minus 9 times the square root of 3. Now, you'll notice we have the same radicals here. This and this are, there's a term for that, it's called like radicals. Similar to the more general term of like terms in algebra. Because they are like radicals, and that is like terms, we can actually add and subtract the quantities together. It's kind of like if I had 5 oranges and wanted to take away 3 oranges from 5 oranges, I could do that and get 2 oranges because oranges are like terms. However, if I was trying to add apples and oranges, that wouldn't be like terms. So we have not 8 minus 9, which is -1. I can drop the 1 and just write -3, root 3. In a similar way, we can do this problem. 16 is easy. That's 2 times 2 times 2 times 2, and then an x. 54 is a bit more of a challenge, but if you remember it's 9 times 6, it's not too bad. 9 is 3 and 3, 6 is 2 and 3. And so we have a cube root of 2 times 3 times 3 times 3, and then at times x times x times x times x. Again, this is a cube root, so you need triples to be able to bring out. Here we end up with 2 cube root of 2x minus Now we notice that these are like radicals, the cube root of 2x. And so because of that, we can actually combine these together. When we do that, we have 2 minus 3x on the front. Times the cube root of 2x, and that is the answer. As we'll see a little bit later, this, if you can remember factoring out a common factor, that's essentially what we're doing. So that'll be when we talk a little bit more about polynomials in a bit. Now, let's have you try an example. So let's have you simplify each of the following radical expressions. And again, go ahead and pause the video. And on the count of 3, I'll reveal the answer. 1, 2, 3. So now you can go through and check your answers. For practice with regards to simplifying radical expressions, be sure to look at pages A23 and A24 of the textbook, problems number 5, 43 through 50. And in our next video, we'll talk about rationalizing a denominator.